The Sun. The most powerful force in our solar system. So huge that more than 1 million Earths would fit inside it. It generates the heat and light that sustains us. Without it, we wouldn't have life on Earth. But our Sun is also violent and volatile, and becoming more dangerous as it ages. It will get hotter and thousands of times brighter. Evaporate away our oceans, melt the surface of our planet, and make any life on Earth impossible. Sunrise, a daily celestial wonder, bringing the heat and light that keeps us alive. We bask in its rays, and yet most of the time, we take the sun for granted. We think it's always been there, and expect it always will be. Our only worry is sunburn. But the truth is very different. The sun can wipe out our most advanced technology, be as powerful as nuclear explosions, and can put our lives at risk. And in the future, as the sun ages, its glorious energy will become a nightmare, driving humans off the face of the planet, potentially threatening our very survival as a species. Understanding what will happen to the sun is something that astronomer Don Brownlee knows about.
The sun lasts a very long time, but it doesn't last forever. All stars have a limited lifetime, just like all people have a limited lifetime.
Our lives on this planet are inextricably linked with the sun's life cycle. But how do we know about the sun's life, when it was born, and when it will die? Especially when scientists are dealing with time spans of billions of years.
No forester ever watches a redwood tree grow for 3,000 or 4,000 years, and yet we absolutely know the trees start as little seedlings, they get bigger, they get giant, and eventually they die. Likewise, see millions of stars in the sky, and you're actually looking at stars in all the stages of evolution.
The sun is a star, just like those that fill the nighttime sky. So looking at other stars reveals fascinating details about our own sun's life. This is a stellar nursery around Orion's belt. Young stars less than 1 million years old are forming here right now, just as our sun did billions of years ago. This sundial represents the life of our sun, traveling from the distant past, starting with the sun's birth at dawn, 6 a.m., through till its death at dusk, 6 p.m. Right now, it is exactly 6 in the morning. The sun is being born. The sun is forming within what scientists call a molecular cloud, the dust and gas debris from hundreds of exploding stars. The molecular cloud is mainly made up of hydrogen, the most common element in the universe. Gravity draws the atoms together, so that over the course of 1 million years, the cloud collapses in on itself. Gradually, more and more material clumps together at the center. It's a bit like when fire dancers make circles. The further away the fire is from their hands, the slower it rotates. If the dancer nearest the camera makes a tighter circle by bringing the fire to the center near her hands, it rotates faster and faster. And it's the same in the molecular cloud. Molecules rotate more quickly in the middle, which becomes denser and denser, until the atoms in the center become so packed, so compressed, they heat up.
As I put compressed air into this model sun, I can feel it heat up, like hydrogen compressing when the sun was forming. And this is how the sun got hot and began the fires that warmed the Earth for billions and billions of years.
The temperature of the cloud soars to millions of degrees, so hot that the hydrogen atoms slam into each other and fuse. Huge explosions of energy are released. The force of these explosions pushes outwards against the force of gravity. Throughout its life, the sun will be in an endless tug of war between these two forces. But now, there's a stalemate. The pressures balance each other. The sun is born. The sun crushes together more than 99% of the original molecular cloud. The little bit that's left then forms the Earth and the other planets in a disk around the sun. Scientists generally agree on this model of how the sun was born. But theory is just theory. The sun is 93 million miles away, which makes real physical evidence hard to come by, at least until now.
3, 2,
August 2001. NASA launches its most ambitious mission to the sun so far, Genesis. At Houston's Johnson Space Center, bringing a piece of the sun back to Earth has been a 10-year dream for Eileen Stansbury.
The chemical composition of the sun is like a fingerprint of the original solar nebula, and being able to catch a piece of sun and bring it to Earth to analyze is exciting.
Stage level still looking good, and we've just went supersonic.
But how do you catch a piece of the sun? Even the outside halo, known as the corona, is up to 3 million degrees Fahrenheit, a temperature no space probe could survive. The answer is to steal a bit of the solar wind, a stream of particles blowing away from the sun at speeds up to 500 miles per second. But the Earth is shielded from the wind by an invisible magnetic force field, the magnetosphere. So until now, we haven't been able to get our hands on it. To get around that problem, the Genesis spacecraft travels deep into space, 1 million miles from Earth. Here, wafer-thin strips of gold, sapphire, silicon, and aluminum, among the purest and most durable materials on Earth, are left to sunbathe in the solar wind. It's a little like dropping marbles into a children's ball pool. Scientists hope as particles in the wind hit the wafers, they will force their way deep inside the layers of molecules within the gold and other materials.
And those marbles will embed themselves within the gaps in the balls. And that's how the solar wind embeds itself within these pure materials.
Meanwhile, down on Earth, the success of a daredevil plan to catch the returning capsule in midair rests on a Hollywood stunt pilot. Fresh off the movie Mission Impossible 3, Cliff Fleming has his own impossible mission to complete. Fleming's task is to hover at an altitude of 10,000 feet, waiting for the capsule to parachute out of the sky.
This pole here was attached to the helicopter. It's about 20 feet long.
Then, Fleming will swoop down 8 feet over the parafoil and grab the 420-pound payload in mid-flight before lowering it safely to the ground. In 5 years of training, Cliff Fleming has a 100% success rate, catching a dummy capsule 11 times in 11 attempts. But these were just rehearsals.
In Hollywood, our film we work on, there's take after take. In this case, there's only one chance.
And having spent over $200 million on the Genesis mission, that one chance to catch the real capsule will be crucial. September 8th, 2004. 3 years after its launch, having collected atoms from the Sun for 884 days, the Genesis capsule begins its journey home. It's the culmination of years of planning and training to ensure that its valuable cargo arrives safely and provides scientists with the purest pieces of the Sun ever to be studied on Earth.
We were anxious.
You had the adrenaline flowing that morning.
I've been working on this mission for a decade.
The capsule re-enters the Earth's atmosphere and, as planned, heads toward the Utah desert where Cliff Fleming is waiting to catch it.
I felt like I was just a center fielder out in a baseball field waiting for the pop fly to come in, and everything was right on time.
Right on time, back in the control room, the capsule comes into view. But something's not right.
It's not supposed to tumble. We knew that something was wrong.
The parafoil is supposed to slow the capsule down, but it hasn't opened. The capsule tumbles out of control, and there's no way that Cliff Fleming can possibly catch it. The capsule hits the ground at over 193 miles an hour. It splits open, and the priceless wafers shatter into thousands of pieces. For the members of the Genesis team, it's potentially a disaster.
Shock, and there was silence.
My whole crew was quiet, and we were disappointed.
And back at NASA, they have a mammoth task ahead to salvage useful results from the mission. Recovering the precious solar samples from the broken gold and sapphire wafers is crucial. The major problem they face is removing the contaminating dirt from the impact, but they hope that the actual samples are still safely embedded deep within the wafers. They also have to ensure that they don't contaminate the samples further. By measuring how much dirt and top layers to remove, the scientists hope to rescue the pure solar samples beneath. These samples are made up of atoms and ions, which are atoms stripped of many of their electrons. They're minute, and the whole sample weighs no more than a few grains of salt.
They're so tiny you can't even see them, but we collected billions of these atoms and ions to analyze.
Most of the Sun is made up of hydrogen, but scientists also expect to find silicon, oxygen, carbon, nitrogen, magnesium, and iron among the billions of atoms they've collected. All the elements are made up of a blend of atoms called isotopes. Scientists already know that some elements blended differently in our solar system. Only the Sun contains the original blend from the molecular cloud from which every other blend came.
It's an exciting opportunity to view back in time to the very beginning, to the birth of our solar system, and try to understand where we came from.
The team has already successfully extracted the first atoms, but it will take time before they can answer all these questions. What they already know is that planet Earth is uniquely located to benefit from the Sun's light and heat, and that is vital for life. We're in the temperate or Goldilocks zone of the solar system. Not too hot like Mercury and Venus, and not too cold like Mars. Instead, it's just right for life to flourish. It's 10 a.m. on our sundial, 4 billion years after the Sun was born. Animals are just appearing. 35 minutes later, humans walk on Earth, our bodies created out of carbon, originally from inside a star. And today, we rely on the Sun for our very survival. Its energy fuels trees and plants, which are essential for the food chain we all depend upon. And by evaporating water from the oceans to form clouds, the Sun supplies us with rain to nourish our crops and fresh water to drink. This energy is created more than 93 million miles away at the heart of the sun's nuclear engine. At temperatures in excess of 27 million degrees Fahrenheit, 4 hydrogen nuclei fuse together to create a single helium nucleus. But the helium is slightly lighter than the 4 hydrogen nuclei, and it's that missing material which is converted under Einstein's famous formula E equals mc squared to pure glowing energy. It's given off as tiny particles of light called photons. Every sunbeam is full of them. Every second, almost 600 million tons of hydrogen are converted into helium. That's more energy in 1 second than 6 billion nuclear power plants would produce in a year. But how does the energy reach us? The incredible journey that photons make to deliver energy to Earth is something David Bodanis, a solar expert, knows all about.
Those photons of light that come down and give you a tan after a while were created over 1 million years ago, and some were starting their journey when the dinosaurs were still around.
They battle their way through the biggest obstacle course in the solar system, starting in the sun's dense core. Here, photons zoom around at the speed of light, bumping into electrons. As they collide, photons pass on energy or momentum, just as one ball does to another on this executive toy.
They pack this terrific punch. It's just like a sequence of balls suspended on wires. If you take one back and whack it into them, the momentum pushes all the way through and makes the one on the far side fly out.
The next obstacle for the survivors is the radiative zone. Here, photons are bounced around by particles of hot hydrogen gas called plasma. They start changing direction in random ways, a bit like balls in a pinball machine, zigzagging around for years and years and years.
The photons in the sun have a journey as hard as these pinballs that spends 1 million years in the radiative zone, and they're hitting against each other all the time, backing sideways, going backwards, occasionally going forward. For some of them, it's been the entire length of time since the sun was formed, and they still haven't made it out.
Only the lucky ones make it out to reach the convection layer, where they get a bit of a rest. In just 3 months, they're absorbed in seething rivers of hot gas and carried by their currents to the sun's surface, the photosphere. Here, the hot atoms enter the sprint section of the course. They cool and release their energy as photons once more. The photons stream into space, and traveling at the speed of light, they complete the 93 million mile journey to Earth in just 8 minutes. Finally, they arrive. Photons have been providing heat and light since the sun started glowing. By 10 a.m., the conditions they helped create gave us animal life on Earth. But where are we today on the sundial? Exactly how old is the sun? Scientists know its age because of one remarkable fact. The sun sings. It doesn't really play a tune, but scientists have discovered that massive pressure changes deep within the sun cause vibrations that resonate through to the surface and bounce around inside the sun like sound waves or seismic waves on Earth. This is the sound of the sun singing. To allow us to hear the sun's voice, scientists speed up the frequency of the sun's oscillating pressure waves 42,000 times and compress 40 days of vibrations into just a few seconds. Work on calculating the sun's age from its singing was carried out at Big Bear Observatory in California by astrophysicist Phil Goody. We know that the sun's temperature and pressure change more and more over time. Phil Goody and his team have worked out that these changes would cause the sun to sing a different song.
This is much like the case of a drum. I put my fingers on and increase the pressure, I get a higher frequency, a higher pitch. And when I take my fingers off, I hear a lower pitch. It's as though the drum, when it ages, it gets softer.
Just like the drum, as the sun ages, changes in its density, pressure, and temperature cause the sun to sing at different pitches. But unlike the drum, which loses pressure as it gets older, the sun's pressure increases, making the pitch higher. Scientists calculated at what pitch they would expect the sun to sing at each stage of its life. Finally, they matched today's song to those calculations to find out its current age.
We've been able to precisely determine the age of the sun to be 4.6 billion years old. So that's kind of a surprise.
Their discovery makes the sun millions of years older than they had previously thought. On our sundial, in which 6 a.m. marks the birth of the sun and 6 p.m. its death, we are now at 10:36 a.m. Humans have only been around for less than a second, and we're reaping all the benefits of its warmth. But it won't always be like that. The sun's heat will slowly increase until it becomes too dangerous for human life. And even today, during the sun's golden age, it already brings many dangers that we are only beginning to understand. Using the latest optical imaging techniques to see what's happening on the surface of the sun, scientists are learning about sunspots, solar flares, and the hurricanes they release into space.
The sun's not alive, but sometimes it has the feeling as though it is because it looks angry.
March 10th, 1989. The sun ejects a giant cloud of charged particles. 3 days later, the solar storm hits the Earth. In Quebec, Canada, 6 million people are about to discover just how angry the sun can be. The sun's warmth and light sustains life on Earth. But it can also play havoc with our modern way of living. Our world depends more and more on technology. Our cities rely on complex networks of power lines, and our communications depend on sophisticated satellites. They can all be wiped out by the sun. Billions of tons of high-energy particles erupting from the sun send powerful storms hurtling through our solar system. Our growing realization of how devastating these storms can be makes the job of space weather forecasters like Larry Coombs ever more significant. At NOAA's Space Environment Center in Boulder, Colorado, they try to predict the sun's violent moods. 1989 brings one of the most dramatic space storms that Larry Coombs has ever seen.
The storms were an eye-opening event for understanding what can happen when the sun has its violent moments.
March 10th, and a telescope in New Mexico captures this solar flare exploding. It sends an electrically charged hurricane toward Earth at a speed of more than 1 million miles an hour. 3 days later, it causes a huge electromagnetic storm over the northern hemisphere. At 2:44 in the morning, Quebec in Canada feels the full force. More than 1 million amps of electrical current overwhelm the power grid. Within seconds, power stations across the province go down like dominoes. 6 million people in Quebec are left without electricity. The blackout lasts for 9 hours. The only light in the sky that night is an unusual pink glow caused by the storm. The events in Quebec cause hundreds of millions of dollars in damages and loss of revenue. Now, the team at Boulder are on Sunwatch. Using live, up-to-the-minute satellite images, operating 24/7, they keep an eye out for any sudden changes in the sun's behavior that can cause disruptions, like in Quebec.
We look at sunspots, and these are these dark, gnarly-looking areas, and this is probably about the size of 14 Earths. We also look at prominences, which is this thing that's sticking out on the side of the sun. Both of these areas can create solar storms.
But how? Scientists believe that the sun's moods are determined by its complex magnetic fields. New magnetic fields are constantly being created because rivers of hot hydrogen gas, called plasma, which are electrically charged, flow at different speeds around the Sun. The Sun's rotation tangles these magnetic lines together, forcing parts of them to emerge on the surface as dark sunspots, and prominences that start sticking out from the surface. The plasma flows and field lines continue to build up as under this sunspot. Eventually, the field lines get so twisted, they snap like rubber bands and cause explosions. So once prominences and sunspots are seen, forecasters are on alert for explosions on the surface of the Sun. Sunspots can be followed by solar flares. These are so powerful that they are like millions of megaton nuclear bombs all exploding at once, sending electrically charged radioactive particles out into space. Prominences just get bigger and bigger. Some end up looking like flares before they too blow up. Both flares and prominences can also be followed by even bigger eruptions in the form of what scientists call coronal mass ejections, or CMEs. When these occur, the Sun discharges billions of tons of electrically charged gas. All these phenomena unleash high-energy particles, which carry electromagnetic fields with them to Earth, and they can disrupt equipment that is electrically conductive, such as a power line. At the California Institute of Technology in Los Angeles, they are trying to understand the science behind the Sun's explosions. Solar physicist Paul Bellin makes his own prominences. He feeds the same ingredients that make up the Sun into a vacuum chamber,
1 kilovolts,
sets up a magnetic field, adds hydrogen plasma, and then drives very large electrical currents along the field.
3 and fire. Our laboratory prominences are a nice human size, about this size. Prominences on the Sun are typically 60,000 miles, and the Sun is just full of them.
Real prominences can grow for days or weeks before they suddenly explode. In the lab, the whole process takes microseconds. But by using a high-speed camera and colorizing the images to see more detail, Bellin's team can watch the effects in slow motion. As the magnetic forces increase, the fields begin to arch and twist up.
And they're really the same as the kinds of forces that you have between magnets. Here, 2 magnets attracting each other, or 2 magnets repelling each other. See, I can't bring them together. So on the Sun, some of these forces are attractive, and they will cause prominences to merge with each other, for example. And the force that makes the prominence blow up is a repulsive force.
Normally, solar wind carries about 1 million tons of electrically charged gas particles away from the Sun every second. But when these explosions occur, the storm clouds of additional particles are more dangerous. The Earth's magnetic field, or magnetosphere, which protects us from solar wind, is overwhelmed. Usually, it deflects the particles toward its weakest point, the poles. Here, they react with oxygen and nitrogen in the atmosphere to create streams of different colors, a phenomenon known as the aurora, or northern and southern lights. But when strange lights appear in the sky away from the poles, as in Quebec, they are a sign of intense solar storms breaching the magnetosphere. Boulder, Colorado, September 6, 2005. Larry Coombs and his colleagues monitor an intense solar storm.
As we're speaking right now, we're having a strong solar flare going on. If we look at the blue image, we can definitely see the energy being blown out from the Sun at millions of miles per hour.
The Sun experiences one of its violent moods, producing explosion after explosion after explosion. Northern lights appear all over America. This time, it's not the power grid that's affected, but communications.
High-frequency communications, radio blackouts are occurring with our aircraft. We're also having problems with satellite phones as well. If we look at our plots up here today, we can see that this activity is affecting the Atlantic and the Pacific. So both ways, communications are blacked out.
We've got 12 in progress.
Everyone wants an update, and the alert status is high, particularly for any airlines that fly near the poles, where the only communication is via high-frequency radio. During solar storms, high-frequency communications can be wiped out, blinding the pilot and risking the lives of passengers.
Great, thank you.
But if airlines get warned, they'll reroute or even ground planes. And it's not just the airlines that fear radio blackouts. Other communication systems can be knocked out. In space, satellites have been damaged, causing loss of signals. Imagine no TV. Imagine all cell phones stop working. But it's not just electrical damage and radio blackouts that these storms can cause. They can also increase the risk of radiation. Solar storm radiation is potentially dangerous for passengers on airplanes. But this radiation poses even greater dangers for astronauts out in space. Late October 2003. 3 huge sunspots appear on the sun's surface, one the size of planet Jupiter. A giant solar flare erupts from the surface of the sun, pointing straight toward Earth. And high above the ground, astronauts on board the International Space Station find themselves directly in the path of the deadly radiation the sun unleashes. Scientists know that the sun was born over 4.5 billion years ago. That's dawn on our sundial. It's now 10:36, and scientists have only learned about solar radiation in less than the last second. We all experience one form of solar radiation. It's sunshine, made up of ultraviolet light. Too much sunshine can cause sunburn and skin cancer. But the ozone layer protects us by blocking out the most harmful effects of UV radiation, and sunblock can do the rest. But there's one place where the type of solar radiation is much harder to protect against. Space. Space travel has always been dangerous. But when astronauts first ventured beyond the Earth's atmosphere,
We're underway. Godspeed, John Glenn.
they were completely unaware of solar storms and the radiation they caused. On August 7th, 1972, Big Bear Observatory in California monitored this flare, unaware of the level of danger. We now know it caused one of the largest solar radiation storms ever recorded. It's a legendary event at NASA because luckily it happened in the gap between Apollo 16's flight to the moon in April and Apollo 17's 8 months later.
You are go for orbit, go for orbit.
Had it occurred during either of these flights, radiation might have killed the astronauts. Scientists know that intense solar storms can be as dangerous to astronauts as the gamma radiation from nuclear blasts. Solar flares release a cascade of high-energy particles known as protons. Protons can pass through the human body, potentially causing chromosome damage and even cancer. Large doses of radiation can be fatal. And today, 30 years after the Apollo missions, NASA relies on space weather forecasts to protect astronauts against these dangers. While training to go into space, like most of us, astronaut Mike Foale had no idea how volatile the sun could be.
I thought I knew about the solar system and the environment, but when they talked about space weather, I went, space weather? What could that be?
Late October 2003. On board the International Space Station, Foal's about to find out exactly how dangerous space weather can be. The sun erupts in a series of events so powerful that they become known as the Halloween storms. October 28th, Boulder, Colorado. At the Space Environment Center, they watched the second largest flare on record explode from the center of the sun.
The problem was the location of it. It was what we would call in the kill zone, where all the energy's coming straight out toward the Earth.
In the line of fire is the International Space Station and Mike Foale. Larry Coombs has to warn NASA.
We were constantly in contact with NASA, as well as they were back and forth with us.
And NASA immediately warned Foale of the danger. They tell him to go to the most protected part of the station, the crew compartment, which is lined with polyethylene shielding. It offers some protection from radiation, although no area is completely safe.
Now you're in survival mode. You just deal with reducing the immediate deathly effects at that moment.
In 2 days, Mike Foale experiences as much radiation as he would normally receive in a week. The equivalent of being bombarded by dozens of X-rays on Earth. But it could have been a lot worse. If he had gone outside during the storm, he would have suffered acute radiation sickness, causing nausea and cellular damage within 10 minutes. There's one solar phenomenon for which there is no protection, and no one knows the cause: a superflare. Superflares are up to 10 million times more energetic than the most powerful solar flares. They can last for up to 1 week and cause stars to shine 1,000 times more brightly than normal. Breck Observatory in Baton Rouge, Louisiana. Looking for flashes of light in the sky is astrophysicist Brad Schaefer. He's found evidence of 9 stars that have produced superflares. At least 2 are almost the same size as our sun. And tonight, he's looking at Omicron Aquila, a star that's just 7% larger than our own sun.
For a 4-day period, this star was 10% brighter than normal. The total power in this flare was 1 million times more power than even the largest flare ever seen on our own sun.
What if our sun ever produces a superflare? What would happen to life on Earth? Schaefer believes everything in space would be fried. On Earth, every power grid would go down. Although the extra heat from a superflare would not in itself be dangerous, doing little more than turning a winter's day into a summer's day. And we'd see auroras all over the world. It might look pretty, but Schaefer fears that the level of radiation from a superflare would be lethal. It would destroy our ozone layer, the very thing that protects us from the sun's ultraviolet radiation.
The dominant killing mechanism is going to come from the radiation from the sun. Now, humans can go around and put on SPF 2000 sunblock and we probably live. We don't go out in the daytime. But our corn crops can't do that. You can't do that for the plankton in the sea. The whales feed upon. The food chain, top, bottom, and middle, they're all going to die.
It sounds scary, but Schaefer is optimistic that we're not at risk. On average, superflare stars have a superflare every century, and there's no evidence that our sun has ever experienced such a flare. But no one knows for sure what causes superflares, though Schaefer does have a theory. He believes that superflares occur if the star has a giant Jupiter-sized planet close by. They each have a number of magnetic fields, which become intertwined as they spin, forming bigger fields between them.
You can imagine my fist is a star, and there will be a planet going around that star. If you have a magnetic field which is attached to the star, I'm going to represent the magnetic field by this rubber band. Well, the magnetic field also can be attached to the planet. As the planet goes around, the rubber band and the magnetic fields are going to stretch and keep stretching, and ultimately they're going to snap, which was a release of energy stored in the rubber band.
If Schaefer's right, We'll avoid the effects of a superflare, but we won't be able to avoid the devastation the sun will cause as it ages. We're currently at 1036 on the sundial. By 1130, it'll be too hot for humans to handle. Our sun is getting hotter. Since its birth 4.5 billion years ago, its brightness has risen by 30%. And scientists predict that it'll get even hotter, evaporating our oceans, melting the surface of the Earth, and ending life as we know it. But how? We know when the sun was born, how it nurtured us, and how it has also thrown a fair amount of danger our way. But that's nothing compared to what happens to life on Earth as the sun heats up and dies, unleashing an inferno that will threaten the survival of humanity on Earth. Death Valley in California, one of the hottest places on the planet. It provides a hint of what the sun holds in store for all of us. Astronomer Don Brownlee shares his vision of that fiery future.
It's an extremely hot day here in Death Valley, but in fact, in the future, the entire planet will become much hotter than this. As the sun ages, it gets brighter and brighter and brighter, about 10% every billion years.
Step into the sun's distant future. The hydrogen fuel is slowly running out, but the nuclear reactions at the heart of the sun are not slowing down. They're speeding up. Pressure at the core drops as the fuel is burned. Lower pressure no longer holds the forces of gravity at bay. Now gravity compresses the core, which heats the hydrogen up even more and makes the fuel burn faster. This increases the pressure coming from the core. The two forces balance again. But it's a cycle that continues as more fuel is burned and the sun gets hotter and hotter.
Eventually, the sun will get so hot, it'll actually melt the surface of our planet, believe it or not.
On our sundial, shadowing the course of the sun's life from its birth at 6 in the morning to its death at 6 p.m., we are now at 10:36 a.m. At the moment, Earth is ideally placed in the solar system. It's not too hot or cold. As the sun heats up, the danger zone will move outwards, scorching the Earth. This will start a catastrophic chain of events that reads like the ultimate disaster movie. We'll lose our jungles, forests, and farmland as the desert grows, turning the surface of the planet into a giant series of sand dunes. Animals will be the first to be hit by the growing heat. They can't protect themselves as easily as humans can. Now things go from bad to worse, much worse. The increased temperature speeds up the removal from the atmosphere of the carbon dioxide that plants need to survive.
Plants virtually disappear from this planet, and anything that eats plants for a living also goes with it.
The glowing heat that gave us life now becomes so strong that it kills off the rich diversity of life on Earth. And as plants disappear, the oxygen they produce declines, making it harder for humans to breathe. We'll also lose most of our food supply. But even at this stage, some humans will probably still be around.
People are very adaptable and very wiry. I think it's very likely that humans could be the last animals on this planet.
Scientists don't agree on the exact date humans will disappear from the face of the Earth. But in 1 billion years from now, at 11:30 a.m. on our sundial, they predict on average it could be as hot as 160 degrees Fahrenheit. By then, the daytime heat could kill us. If we're still around, we may live underground and only come out at night.
People have two options. We can build more and more sophisticated artificial environments on our own planet, or we can potentially go elsewhere. I know it's a common belief that we are destined to live somewhere in the outer solar system.
If we're going to survive as a species, we are going to have to find a new home, especially once the Earth's water starts to vanish. As the sun keeps getting hotter, Earth also gets hotter, and more water evaporates until all our oceans disappear. And it's this disaster that will make human life on Earth impossible. In Death Valley, the lake at Badwater dried out 10,000 years ago, leaving just salt flats. It's an eerie foreshadowing of what's to come.
I would describe this area as totally alien. It looks like we're on a different planet, but it's our planet, and all of our planet will look like this.
And from space, it will look alien too. Gone will be the blue and white planet covered with water and vegetation, to be replaced by a planet that looks more like Mars. By now, we need to be long gone from the neighborhood, moved to another planet, mere spectators to what the sun does next. Now the sun swells and changes color from yellow to red. It is becoming what astronomers call a red giant, an old star entering the last stage of its life. It completely fills the daytime sky. The atmosphere has gone, and it's like looking into space. It is some 6.5 billion years from now. On our sundial, we are nearing dusk. And though the sun's now a senior citizen, it's more active than ever. Now the sun uses up the last of its hydrogen fuel in the core. It's burning helium, which burns ever hotter. The energy radiating out from the superheated core pushes the upper layers of the sun outwards, making it bigger and bigger. As it grows, the surface gradually cools, making it appear redder in color. Although the outer layers of the sun are cooling, the sun is reaching out toward us across the solar system. And just like stepping closer and closer to a fire, the Earth feels more and more heat.
When the sun becomes a red giant, it's a dangerous phase for a planet like the Earth. It's quite spectacular. It becomes very much brighter, very much larger. Its heat will fry the Earth.
By now, the surface of the Earth has long melted, but there's worse to come as the sun becomes more and more unstable. Violent thermal pulses of heat mean that the sun goes into overdrive. Its diameter expands 1,000-fold.
During some of these pulses, it expands out to basically the size of the Earth's orbit, and it will swallow the inner planets.
Anything in its path is vaporized. First, Mercury burns up like a giant meteor. Venus will be next. But what about Earth? Will the home that has sheltered us for millions of years suffer the fate of its neighbors? As waves of heat tear through the sun, it sheds billions and billions of tons of material into space, and its gravitational pull weakens. This may just allow the Earth to move away from the sun and escape incineration. But scientists don't know for sure, and even if Earth escapes a fiery end, it is by now an unrecognizable molten planet. It's approaching 6 p.m., dusk on our sundial, and the sun's life as a burning star is over. But it's not big enough to blow up and become a supernova. Only superstars, over 8 times as massive as our sun, explode. Eventually, it shrinks into a white dwarf, living on for hundreds of billions of years, but only producing a faint glow. So this is the way the sun ends, not with a bang, but a whimper.
The wonderful sun that provided the Earth heat and energy for billions of years will end up being a small star not much larger than the Earth.
The sun gave us life. With its death, all life on Earth will be gone. If humans still exist, we'll be somewhere among the stars. So next time you're on that beach enjoying the sun, remember, it won't last forever.